For part A, I want to take the derivative of sine of 2x. So I'm just going to write this with some parentheses. So I'm not taking the derivative yet, I'm just rewriting the function. So I see this as a composition, and it's sine of 2x. I need to use the chain rule to take the derivative. So the idea is you ignore this part and just think about taking the derivative of the sine function. The derivative of sine goes to cosine, and we just leave the 2x alone. Now, since this wasn't just x, the chain rule says we have to multiply by the derivative of 2x, which is 2. And that's the answer. For part B, we're dealing with the function e to the 9x. Again, identifying the composition. All right, so if you want to take the derivative of the function e to a power is e to that power. It is its own derivative. But since it's 9x, I have to multiply by the derivative of 9x, which is 9. For the function g of x equals sine to the 10th power of x, this is sine of x to the 10th power. And here again, we have another composition of two functions. So to start with, how would you take the derivative of a variable to a power? The way that works is, if we're taking the derivative of g, you would bring the 10 down front, you would copy down your variable, and you would subtract 1 from the exponent. But by the chain rule, you need to multiply by the derivative of sine, which is cosine. There's a little typo here in part D. That variable x really should be y. I'm going to rewrite this function a little bit. First, in a couple of ways. That divided by 3 is equivalent to saying you're multiplying the tangent function by a third. And for emphasis, I'm going to put pi y in the parentheses. So here's my composition. It's the pi y. So when I take the derivative h prime of y, I write down the 1/3, and I multiply by the derivative of tangent, which is secant squared, and I leave the pi y alone. But by the chain rule, I multiply by the derivative of pi y, which is pi. For e, let's see, we have x cubed plus x to the power of 8. So again, I'm seeing that the composition is, well, I have something to a power, and so that's how I'm going to start by taking the derivative. F prime of x is equal to, okay, I bring down the 8, I copy down my variable, and I subtract 1 from the exponent. By the chain rule, I have to multiply by the derivative of this thing. I would get 3x squared plus 1. And that's it. For this function g of t equals the square root of 1 plus tangent of t, I'm going to replace the square root with a power of 1/2 and just copy down the 1 plus tangent of my variable t. So my composition is this. So to start with, if you want to take the derivative, I'm thinking it's a variable to an exponent. So I'll bring down the half, I'll copy down my variable, and I'll subtract 1 from the exponent. A half minus 1 is negative 1/2. But by the chain rule, I need to multiply by the derivative of this thing. The derivative of 1 is 0. The derivative of tangent of t is secant squared of the variable t. And that's it. All right, so taking the derivative of this function f of x, I'm going to choose to write this as not a fraction, but something to the negative 3rd power. I can move this entire piece to the numerator if I make that exponent negative, but I will leave 1 minus x squared alone. So I'm taking the derivative of, again, something to a power, and the rule we have for this is if you want to take the derivative, we bring the negative 3 down front, copy down the variable, the inside part, subtract 1 from the exponent, but by the chain rule, I need to multiply by the derivative of this thing. The derivative of 1 is 0, I won't write it. Then we have minus the derivative of x, so we get minus 1, and minus the derivative of x squared, which is 2x, And that's the answer. All right, so here we're taking the derivative of secant of 2z plus 1. So my variable is z, just rewriting the function. And my composition is, okay, I have 2z plus 1 composed inside my function. To start taking the derivative of this thing, f prime of z, I need to know what is the derivative of secant. Our formula for it was it's secant of your variable times tangent of your variable. Now the thing that goes in the parentheses is equal to what is here. So I'm just going to copy down that 2z plus 1. Now by the chain rule at the very end of this, we now have to adjust by multiplying by the derivative of 2z plus 1. The derivative of 1 is 0, and the derivative of 2z is 2. And this is the answer. All right, so here we're differentiating sine of x plus 1 to the 2/3. It's not written, but that 1 is not within the sine function, so I'll just put some parentheses for a little bit of emphasis. If I'm taking the derivative of this function, I see I have a variable, again, to a power. So the derivative will be bring down the 2/3, copy down the inside part, which is sine of x plus 1. And if I subtract 1 from 2/3, I get negative 1/3. By the chain rule, I need to multiply by the derivative of what's inside. That 1 goes to 0, and the derivative of sine is cosine. And that's it. I see a couple of ways to take the derivative of this. One, you could put e to the negative theta into the denominator, making it e to the theta, and then you could use the quotient rule. But here, I think the approach that I'll take is leave it as is and use the product rule. So I see that we have this first piece and this second piece. So to start with, if I want the derivative of z with respect to theta, the product rule says take the derivative of theta, and that'd be 1. And then we copy down e to the negative theta. That just stays as is. I then add on. I leave the first thing alone, but I now take the derivative of e to the negative theta. And I'm noticing that, well, it's a composition of two functions. So it's like really negative 1 theta. So if I want the derivative of this thing, it'll be e to the negative, I'll just put negative theta. But by the chain rule, since it wasn't just theta, it was negative theta, I have to multiply by negative 1. This negative 1 came from the number that is in front of the theta. And here's the answer. So now we're differentiating some functions using just a different notation. d dx means take the derivative of this thing. All right, when I look at this problem, I'm seeing a product of two functions. So we have 5x plus 1 squared. I know how to take the entire derivative of that thing. And then I have cosine of x by itself, and I know how to take the derivative of that part too. So if I'm taking the derivative by the product rule, I first start by taking the derivative of 5x plus 1 all squared. I need the chain rule on this piece. So if you're dealing with just the 5x plus 1 squared part, it is definitely a composition of two functions. So my derivative of just that first part is I bring down the 2, I copy down the 5x plus 1, I subtract 1 from the exponent, I'll put it there for emphasis, and I multiply by the derivative of just 5x plus 1, which is 5. There it is, the derivative of the first part. I then multiply by, leave the second part alone. I then add on, okay, I'll leave the first part alone, and now I need to multiply by the derivative of the second piece. And if I look at the second piece, it's not a composition of two functions. I don't need to use the chain rule here. I just know that the derivative of cosine is negative sine. So unsimplified, here's my answer. All right, here we're taking the derivative of 1 minus t to the 5th times 1 minus 2t to the power of 3. Again, I'm noticing that we have a product of two functions. And this time in both parts of the product, we have a composition of two functions. So if I think about those parts separately, I have 1 minus t to the fifth, and I also have 1 minus 2t to the third. So when it comes to taking each of those parts individually, there are compositions, and therefore the chain rule must be used. So when I take the derivative, I start with the derivative of this first part, which is the derivative of this. Okay, I'll bring the 5 down front. I will copy down the 1 minus t. I'll subtract 1 from the exponent, but I have to multiply by something. The derivative of 1 is 0. The derivative of negative t is negative 1. So it's really multiplying by negative 1. I then continue by just copying down the second part. I then add on, leave the first part alone, but multiply by the derivative of the second thing, which is the derivative of this. I have a variable to a power, so we get 3, copy down the inside, subtract 1 from the exponent, and I multiply this whole thing by the derivative of 1 minus 2t. The 1 goes to 0, and negative 2t has a derivative of negative 2. And here's my answer. Here we want to take the derivative of the square root of 1 minus cosecant theta with respect to theta. So we're switching the variable here. And just a little work beforehand, I'm really saying this is 1 minus cosecant of theta to the 1/2 power. Definitely a chain rule problem because we have a composition of two functions. So if we go to take the derivative, we're going to bring down the 1/2, copy down the inside, subtract 1 from the exponent. 1/2 minus 1 is negative 1/2. And then we multiply by the derivative of the inside part. The 1 goes to 0. I'll include the negative. What is the derivative of cosecant of theta? So off to the side, cosecant of theta. This is negative cosecant theta times cotangent of theta. So we can prove this by using the quotient rule, but I'm just going to simply plug this information directly here. So we get two negatives. It's negative times this negative cosecant of theta times cotangent of theta. So you can even put like some extra parentheses in there to say we're multiplying these two negatives together. And what this means is the answer is 1/2 times 1 minus cosecant of theta to the negative 1/2. And those two negatives are unnecessary, so I'll just put cosecant theta times cotangent of theta, and that's my answer. Also, I'm noticing something. This here is not a true statement, but if I put the derivative symbol in front of this, okay, this is now true. This looks really similar to the previous problem, except I see the square root is now in a denominator. The derivative with respect to theta would be, well, I know this really means, if I'm just rewriting the function itself, it's 1 minus cosecant theta all to the 1/2 power, completely in the denominator. You could use the quotient rule here. I think it is more convenient to bring that whole thing up to the numerator, but make the exponent negative. So we have a composition of two functions, and we're thinking ahead. I know I'll have to take the derivative of the cosecant of theta part, which the rule is it's negative cosecant theta times cotangent of theta. Let's put all of this together. If I take the derivative of the function from here, I'll put that over here. We would bring down the negative 1/2, so we get negative 1/2. Copy down the inside part. Subtract 1 from the exponent. Okay, so 1 from negative 1/2 is negative 3/2. By the chain rule, I multiply by the derivative of 1 minus cosecant theta. The 1 goes to 0. I won't write it. We have a negative, and then the derivative of this thing, which is this. We have a negative, negative. So there's going to be, well, we're subtracting off the derivative, which also has a negative in it. So we're really multiplying that stuff together. And the two negatives do cancel. So I'll put my answer as this. And that's it. All right, here's the derivative of 10 to the power of 1 minus tangent of theta. I don't like how the exponents aren't a little bit more well-defined here. This is 10 to the power of 1 minus tangent of x. And here we're saying this entire thing is in the exponent of 10. The rule that we have for exponential functions is, well, you get the same function back. You get 10 to the 1 minus tangent of x, but you also have to multiply by the natural log of the base, which is the natural log of 10. But by the chain rule, we need to multiply by the derivative of 1 minus tangent of x. The derivative of 1 is 0, so we get negative, well, the derivative of tangent is secant squared of x, and this is the answer. All right, so here we're taking the derivative with respect to the variable y of tangent of cosine of y. And definitely a composition of two functions. Cosine of y is being composed within place of tangent. So if we're taking the derivative starting with tangent, we get secant squared of, and we just copy down that cosine y. By the chain rule, I need to multiply by the derivative of cosine of y, which is negative sine of y. And this is the answer. In this problem, I'm seeing a square root, which automatically makes me think, why don't we replace this with a 1/2 exponent? So it's all this stuff to the 1/2 power, and the stuff is x plus 1 divided by x minus 1. Another composition, so I have some variable to a power, so I know how to start this problem. It's going to look a little different with that fraction inside there, but you bring down the 1/2, copy down all of the stuff on the inside, and then we subtract 1 from the exponent. 1 taken from 1/2 is negative 1/2. But now by the chain rule, you have to multiply by the derivative of just this part, the derivative of this fraction. It's a fraction. I think I'm going to actually use the quotient rule here, and I'm focusing just on this part. I'm taking the derivative of this thing. All right, so using the quotient rule, I'm going to set up this giant fraction, and the quotient rule said start by taking the derivative of the top, and the derivative of the top is 1. And then we multiply by the bottom, which is x minus 1. We then reverse this, we subtract off, okay, leave the top alone, but then multiply by the derivative of the bottom, and the derivative of the bottom is also 1. This whole thing is divided by that denominator, x minus 1 squared, and this is our final answer. I think this one might be worth simplifying, so I'm actually going to go through that process. If you got to here, hey, fantastic, that's great. I'm actually going to try to combine some like terms and stuff like that. To start with, this negative 1/2 can be applied to both the numerator and the denominator. So I'm going to think about this first piece as, well, we got 1/2. That fraction is really x plus 1 to the negative 1/2 over x minus 1 to the negative 1/2. In my fraction over here, I have x minus 1 squared. If I think about what is in the numerator, let's see. This stuff here is really just x minus 1. I don't need this 1 or the parentheses, so I'll just go ahead and write that down. This is x minus 1. Over here, I don't need to write this 1, but I do need to distribute this negative, so this negative will go to both terms. It'll become negative x and then minus 1. So in terms about thinking about, the stuff that cancels, this cancels with that, and those two negative 1s really becomes negative 2. So let's see. I guess what I'll do is I'm going to put this in the denominator and this in the numerator and make both of the exponents positive. I'll combine those two numbers. Let's see what we get. We have 1/2 okay, we get x minus 1 to the positive 1/2 and x plus 1 to the positive 1/2. And in this fraction, we have negative 2 and then also x minus 1 squared. More stuff cancels. This cancels with the 1/2, and it does leave us with the whole thing being negative. And also, we have an x minus 1 in the top and bottom, meaning that we can subtract those two exponents. Let's try that. Okay, this whole thing it's negative. I'll leave the x plus 1 to the 1/2 alone. I'm not doing anything to that. But the x minus 1 as an exponent, that is 1/2 minus 2. Between the numerator and the denominator, we have like bases, so I can subtract those exponents. Let's see, 1/2 minus 2 is going to be negative 3/2. So here's what we get next. We get negative x minus 1 to the negative 3/2 over x plus 1 to the 1/2. I'll make that exponent positive. So this is really x minus 1 to the positive 3/2 times x plus 1 to the 1/2. So there's the answer, like really simplified. You could also express things with root symbols instead of using fractions for the exponents. That first thing is going to be the square root of x minus 1 cubed, and that second piece would just be the square root of x plus 1. So in terms of simplifying this problem, either of these are acceptable. But hey, for what we're doing here, like this answer is good. And that's it. What is the derivative of, write this a little bigger, we have e to the 2x divided by e to the x plus e to the negative x. Where to start? Well, I'm noticing we have this giant fraction. So if you start by taking the derivative of this thing, we'd have to start with the quotient rule. And that means we'll have to take the derivative of both the numerator and the denominator separately. And I'm noticing in both the numerator and the denominator, there's compositions of functions. There isn't one here, but those two, definitely we have a 2 and a negative 1, so I'll have to be careful in taking the derivatives of those pieces. So to start with, we are using the quotient rule. So I'll set big fraction. Step 1 is to take the derivative of the top. The derivative of e to a power is e to that power. But since there's a 2x instead of an x, I have to multiply by 2. I then take that thing and just simply multiply it to the denominator. I then subtract off. Okay, now I leave the top alone and take the derivative of the denominator. When I take the derivative of this e to the x, nothing happens to it. But when I take the derivative of this thing, I get e to the negative x, but I have to multiply by negative 1. Looking good so far. I simply would then just square the denominator, this thing. I think this one might be worth simplifying too. In fact, for all these problems, it might be worth just going through trying to simplify it just so you get some practice with that. But this answer, totally fine. But what I'm going to do is, let's see, I can factor a 2x out from both of these giant terms. I can distribute this 2 into the parentheses and make this a negative e to the negative x instead of putting this negative 1 here. Let's put all that together. So if you factor out e to the 2x, and you also at the same time multiply in this 2, we would have 2e to the x plus 2e to the negative x. All right, over here, this is gone. This is e to the x, and this is minus e to the minus x. But we're also making both of those things the opposite sign when we distribute in this negative. What does this all mean? Okay, nothing happened to this e to the x. This is gone. This makes it negative e to the x. So we get negative e to the x. This piece becomes negative e to the negative x, but this negative makes it a positive, and so great, we get positive e to the negative x. Wonderful. And then in the denominator, we still have e to the x plus e to the negative x all squared. Looking good here. Any like terms? Yeah. We have an e to the 2e to the x, and we're subtracting 1, so we're just left with e to the x. Then we have 2e to the negative x, and we're adding 1 more to it, so this would go up to 3. So what do we have? I would write this as, well, we got e to the 2x multiplied by e to the x plus 3e to the negative x all over e to the x plus e to the negative x, and that whole thing's squared. I don't really see any point to taking it further than this. That looks pretty good. This answer, that's fine. But here's some practice if you decide to simplify. In question 3, we're still taking derivatives, but for here, we have to apply the chain rule a couple of times if there's more than just a single composition. And if I just read this one, let me rewrite it. So we're taking the derivative of, okay, we got 1 plus sine of, and I'm saying of, and that means composition, so it's 1 plus sine of 2x, all to the power of 3. So if I start this one, well, I know, all right, I'm just taking the derivative of something to the power of 3. Let's start there. Okay, we would bring down the 3, copy down that inside stuff, that's 1 plus sine of 2x, and then we subtract 1 from the exponent. However, by the chain rule to complete this problem, I now need to take the derivative of the inside part. Let me just write that down here. We're now taking the derivative of 1 plus sine of 2x. So we're now just differentiating that. And we got a composition. That means when you take its derivative, I know the 1 goes to 0, sine goes to cosine of 2x, but by the chain rule, that 2 has to come out. So going back and kind of thinking about this problem at the beginning, when I take the derivative of just the part in this rectangle, I know we'll have to multiply the whole thing by the derivative of 2x, which is 2. Let's put that here. Okay, the derivative of 1 is 0. I won't write it. The derivative of sine, again, goes to cosine of 2x. But by the chain rule, the 2 is coming out. There were 2 compositions I saw here. Something composed in the power of 3. That's why this piece ended up here. But at the same time, I saw another composition here, and that's where this 2 came from. Are there 2 compositions in taking the derivative of tangent squared of 3x? And yeah, the answer is yes. This is the derivative of, well, that tangent squared really means we're taking tangent of 3x and we're squaring it. So the initial composition I notice is, oh, we have something to the power of 2. But at the same time, when you take the derivative of this tangent of 3x, well, I got to deal with the composition that's within tangent, which is a 3x. Let's try working through this one. So it's like all this stuff I'm just kind of ignoring. I'm thinking of something to the power of 2. So I bring down that 2. I copy down that variable part, the tangent of 3x, and I subtract 1 from the exponent. Now here's where we start applying the chain rule. Now it's time to go back and think about all this stuff here. Well, tangent, if I take the derivative of a tangent function, I get secant squared. And the variable part, the 3x, just tags along. Now finally, I have to deal with this 3x. It was composed within tangent, the thing I just took the derivative of, and so therefore I'm going to put a 3 right here. All right, so I'm going to multiply by 3. And this is the answer. All right, so the derivative of 4 to the power of sine of 10x. definitely a couple of compositions. We have 4 to a power, but within that exponent, again, we got this composition. If we take the derivative of 4 to a power, you get 4 to that power, whatever the power is. Just copy it down. But since we're dealing with 4 to a power, the derivative rule says you have to also multiply by the natural log of 4. Now here's where the chain rule comes in. You have to take the derivative of sine of 10x. Well, if you start with sine, the derivative of sine is cosine. But since we're taking the derivative of sine of 10x, the derivative of 10x is 10. So we get this value here. This is the derivative. Here we're taking the derivative of e to the power of sine of 1 over x. Just thinking down the way here, I know eventually we're going to have to deal with this derivative of just the 1 over x part. It looks like a fraction. You might think quotient rule. I don't know. I think it might be a better idea to think about taking the derivative of e to sine of, and I'll put this as x to the negative 1. 1 over x and x to the negative 1 are equivalent, but written this way, it's just a little bit quicker to take the derivative. So e is composed with a function, but sine is composed with a function as well. When it comes to taking the derivative, I focus on just the e part of this, and the derivative of e to anything is e to that thing. Technically, you'd, I guess, put the natural log of e after this, but natural log of e is 1, so we don't write it. Now, we take the derivative of the sine function part. So now I'm just focusing on this. The derivative of sine of whatever must go to cosine of that variable. But since that variable is not just x, it is x to the negative 1, I need to again multiply by the derivative of, okay, for x to the negative 1, I bring down the negative 1, which I'll just put as negative, copy down the x, subtract 1 from the exponent, and here it is. This is the derivative. All right, question 4. More just practice with using the chain rule, taking derivatives. These might be hard. I don't know. Let's see. I have y is equal to sine of x. I'll just write this so it's a little bit bigger. Just rewriting the function. So this is sine of, and within that function is sine, but within that function is also sine of x. So when it comes to taking the derivative, for the time being, just kind of like ignoring all of this stuff. I know by the chain rule I'll have to eventually multiply it by its derivative, but the derivative of just this thing, well, I'll have to use the chain rule on that thing again. All right, so here, I'm calling this my function y, so I'm going to do d dx of both sides. So that is dy dx, the derivative, is equal to, okay, well that first sine becomes cosine, and it's just cosine of all the stuff in the parentheses. But by the chain rule, so I'm now ignoring this part and this part, but I'm thinking of, all right, what's the derivative of this thing? That's going to go here. Well, the derivative of sine of anything, oh, well, this thing also goes to cosine, so it's going to be cosine of sine of x. But, again, by the chain rule, I have this sine of x here. Chain rule says I have to multiply by the derivative of sine of x, which is cosine of x. There was no composition to worry about here, so the process ends. And here's our answer. The answer is cosine of sine of x times cosine of sine of x times cosine. Okay, how do I take the derivative of this thing? I'm seeing a bunch of square roots, and every time I replace those with powers of a half. So I guess to start with, I mean, this main square root means I'm taking all of this stuff and raising it to the 1/2 power. So I'm just going to copy this stuff down in the parentheses. So it's going to be x plus, okay, now we get to this other square root. So again, I'm going to replace this part with also something to the 1/2 power. So I'll get some parentheses. It's going to be something to the 1/2. And if I copy down, it'll be x plus, okay, we get to this last square root, it's just the square root of x. It has no composition, so it'll be also x to the 1/2 power. Here it is. It is x plus quantity, x plus square root of 1/2. Oh man, this is even really hard to say. I don't know how you'd say this thing. Who cares? I want to take the derivative of it. Now, you can't like multiply these 1/2s together because this 1/2 applies to this, but also this thing here. You got to leave it just like this, I think, to take the derivative. Using my approach here, I'm just going to pretend that that is acting as x, and this is how I'll begin. All right, great. All right, so if I find dy dx, if I find that, okay, start by bringing down the 1/2, and then copy down all that stuff that is inside the parentheses. And I subtract 1 from the exponent, which gives me negative 1/2. But by the chain rule, I now multiply by the derivative of just this part. Well, I'd start with this x, and the derivative of that is 1. Then you'd add on, okay, now I'm taking the derivative of this part. Again, we got this second composition, this thing. Works the same way where, all right, I'll bring the 1/2 down front, copy this down, subtract 1 from the exponent. Let's do it. Okay, so we bring down the 1/2, copy down the x plus x to the 1/2. We subtract 1 from the exponent. But again, by the chain rule, we're multiplying by the derivative of this thing. Now, I'm not setting up another set of parentheses and putting that outside of there because we have this 1 here. I started by taking the derivative of this x, which gave me 1, and then I jumped over to this piece. I brought down the 1/2, copied down the inside, subtracted 1 from the exponent. But the chain rule says, okay, we're going to put whatever comes from here attached just to this piece. What comes out? Well, the derivative of x is 1, and then we add on the derivative of whatever x to the 1/2 is, and that's going to be 1/2 x to the negative 1/2, and I'll close parentheses. The only other set of open parentheses we have is right here, so I'll put this like that, and here's my answer. I'm not even going to try to say it. I was going to, but I don't know. Here it is. Good enough. You can simplify it if you want to try. Go for it. But that's all. I'm now regretting writing these problems down. But anyways, I want to take the derivative of y is equal to 1 over 1 plus 1 over 1 plus 1 over x. Okay, when dealing with fractions like this, I think what I'm going to do is not try to use the quotient rule. But what we can do is take this whole thing and bring it up to the numerator if we make the exponent on the denominator negative 1. So let me try to talk through that. So all of this stuff here, I'm going to bring to the top and put a negative 1 exponent on the whole thing. And that would be 1 plus 1 over 1 plus 1 over x, all to the negative 1. But I think I'm going to do the same thing here. I know I'll eventually have to take the derivative of this inside thing, so I'm going to take this whole thing, move it up to this exponent, but put a negative 1 exponent on that. So this is also equal to 1 plus, okay, now we have 1 plus 1 over x, that whole thing to the negative 1, and that whole thing to the negative 1. And okay, again, we have this 1 over x, so I'm going to bring a negative 1, or I'm going to put this x in the numerator with a negative 1 exponent. So my function y is really equal to 1 plus x to the negative 1, that thing to the negative 1, and then this whole thing to the negative 1. Not the derivative, but this thing is another way to write this function. It's just written in a way I think that's easier to apply our derivative rules. All right. Well, I see this as it's something to a power, so I'll begin there. I'm going to find dy dx. I'll begin by bringing that negative 1 down front, and I'll just put negative. It's negative 1 plus 1 plus x to the negative 1 all to the negative 1. That whole thing, I'm subtracting 1 from the exponent here, and that gives me negative 2. I then multiply this whole thing by the derivative of this part. Now the derivative of that 1 is 0. I won't write it. I'll pick up with this part here. So open up some parentheses. Taking the derivative of this thing, I'll bring the negative down front. So I get, just put negative. Then we get 1 plus x to the negative 1. That whole thing to the negative 2. But again, we have this other composition. So I'm going to multiply this piece that I got here by the derivative of this thing. The 1 goes to 0. But when I get to the x, I get negative x to the negative 2. And I'll close parentheses, and then I'll close the parentheses again. And this is the answer. I'm seeing there's some things that could be simplified, like, that negative could be multiplied with this one. That means the entire answer will have a negative in front of it. You could start making exponents positive if you'd like to. I'm going to leave my answer just as this. And saving the best for last, this one here, y is equal to, this thing is referred to as a power tower, where you just keep putting exponents within the exponents. Maybe just before trying to differentiate this problem, written this way, we have to be careful with what it means. Okay, this really means when you don't see any parentheses in a power tower, in terms of order of operation, you would compute what's in this exponent first, then deal with the exponent on 5, then the exponent on 4 and 3 until you get down to this 2. I guess all I'm trying to say is, if you're putting parentheses in here, this is really 2 to the, and then you got some, parentheses, to the 3 to the parentheses, to the 4 to the parentheses, to the 5, and then there's an x squared within that 5. Close those parentheses, close those parentheses, close those parentheses. This is a mess written this way, but this is what it means by the power tower. You're working from the top down. You would not just simply multiply all of these exponents together and do like 3 times 4 times 5 times x times 2. Like, you would not think about it this way. This is what it means. And written this way, okay, definitely if you take the derivative, you have to use the chain rule. It's going to be 2 to whatever this thing is. You take the derivative of that. So let's start. Let's find dy dx. Okay, 2 to a power, its derivative is 2 to that power. That's 2 to the 3, to the 4, to the 5 to the x squared. But then you multiply by the natural log of just the base, which is the natural log of 2. However, by the chain rule, you would have to multiply by the derivative of what appears within this box. Again, it's 3 to a power. It's a complicated power, but that just means we're going to have to use the chain rule again. I'll now treat this whole thing as just a single variable and deal with 3 to the power. So the derivative of 3 to a power is 3 to that power. That's 3 to the 4 to the 5 to the x squared. And you'd multiply by the natural log of the base, which is the natural log of 3. Wonderful. But by the chain rule, you have to multiply by the derivative of what is in the exponent, which is 4 to a power. All right, I'll try to write that in here. Well, 4 to a power, I know how to take the derivative of that thing. Okay, 4 to a power, its derivative is, well, it's 4 to that power. That's 4 to the 5 to the x squared. But by the, and you got to multiply by the natural log of 4. But by the chain rule, you also have to multiply by the derivative of what is in the exponent, which is also a composition of 2 functions. I'm kind of running out of different colors to use. But this time, I now have to multiply this whole thing by the derivative of what was in the exponent. What do we get for that? The derivative of that's going to be, well, it's 5 to its power times the natural log of 5. But the thing within the exponent was x squared. That's not a composition. That means this process will actually stop here. I need to multiply this whole thing by the derivative of x squared, and that'll be 2x. And here it is. This is the derivative of this function here.